Hello dear students, so let's discuss question number 6 of INMO 2025. So let's first read the question. So in this we have given let b is greater than equal to 2 is a positive integer and Anu has an infinite collection of notes with exactly b minus 1 copies of a note worth b power k minus 1 rupees for every integer k greater than equal to 1. So we have b greater than equal to 2 and k is greater than equal to 1. Right, now next thing is, and each node we have a b minus 1 copies worth b power k minus 1. So if we see for k is equal to 1, b power k minus 1 is b minus 1, and for k is 2 it is b square minus 1, and so on. So that we have given a positive integer n is called payable if Anu can pay exactly n square plus 1 rupees by using some collection of her notes. So prove that if there is a payable number, then there are infinite many payable number. By assuming that if there is a payable number, we have to prove that there are infinite many. Now first of all, we can say that a number n square plus 1, if we say we have a number n which is payable, so I can say n square plus 1 is equal to combination of these values, right? And we also know that each of them, each quantity of these rupee, what we can say, these rupees is b minus 1 copies each. So if I say I use a1 copies of b minus 1, a2 copies of b square minus 2, and let's say I'm saying that we use up to b power m minus 1, right? तो लेट्स से हमने b पावर m माइनस 1 वर्थ रुपीज तक के नोट को यूज करके n स्क्र प्लस 1 को के इक्वेट कर दिया. लेट्स से ये है हमारे पास n स्क्र प्लस 1 अगर अचीवेबल है, मीन्स अगर हम कह रहे हैं कि ये हम बना सकते हैं n स्क्र प्लस 1 रुपीज यूजिंग दिस. अब यहाँ से और एक चीज और है कंडीशन a1 a2 am पे कि ये जो a1 a2 और am सारी वैल्यूज हैं ये हैं 0 से b माइनस 1 तक ना. तो अगर आप यार ये चीज देखो, जो कंडीशन इन पे दी हुई है a1 a2 am एक्सेट्रा पे 0 से b माइनस 1, और अगर मैं b में इसको एक नंबर अज्यूम कर लूँ लाइक a1 b a2 b स्क्वायर अप टू am bm b पावर m this minus a1 up to am. So I can say that, so this is a number in a base b, no? It represents a number in a base b, and I can write it as a am minus 1 a1 0, no? In a base b, and the second part is summation of that digits of a number is equal to n square plus 1. So basically n square plus 1 is representing the number minus sum of its digits, no? A number which is we are representing in a base b minus sum of its digits, and we know that this is divisible by b minus 1. जैसे कि हमें 9 की डिविजिबिलिटी का क्राइटेरिया पता है कि जो 9 की डिविजिबिलिटी है वो था सम ऑफ नंबर माइनस सम ऑफ डिजिट्स, सो दैट इज इन बेस 10 ना. अगर हमारे पास बेस b है, so I can say that the left hand side is divisible by b minus 1, and in fact right hand side is also divisible by b minus 1, and you can say the same thing from this side also. Okay, this is 1, not a 2. So you can see in all these factors you have a b minus 1 common, so you can see right hand side is a multiple of b minus 1, so the left hand side should also be divisible by b minus 1. So one thing that we get from there is that n square plus 1 should be divisible by b minus 1, or I can say n square plus 1 is 0, mod of b minus 1, or n square is congruent to minus 1 mod of b minus 1. Now if you see, this condition is true, always true for b is equal to 2. Now for b is equal to 2, this is always true. If you put b is 2, so it is mod of 1, and you can see n square plus 1 is always divisible by 1. So I can say that I will always write n square plus 1 type number in base 2 using this, that a number minus sum of its digits. And in fact, there are infinite many such numbers. We can say that. Now let's try to prove it, that in a base 2 we have a infinite such numbers. Now if you pick the right hand side of our expression, that is am up to a1 0, so this is basically the number minus its digit sum. Now if we try to make a square, like, and we are using base 2, so here base is 2. So if I am writing one number 2 power 2m, so I can say it is 1 into 2 power 2m, right? So if I pick this number, then summation of ai is minus 1, na? Because 2 power 2m number has a sum of digit is 1. Now this is not a perfect square, so further I can use 2 power m plus 1. Again I add one more term having coefficient is 1, so its digit is 1, so I can say this is the corresponding digit of 2 power m plus 1 is 1. Like if we take an example, if I say 2 power 3, it is basically 1 0 0 0, na? So sum of digits you can see it is 1. If I use 2 cube plus 2, so that will become 1 0 1 0. So sum of digits are 1 plus 1. So same thing I am doing here, that if I use these two as a number, 2 power 2m plus 2 power m plus 1, then the corresponding digits are 1 and 1. So you can see here. So now if you see the two terms, 2 power 2m plus 2 power m plus 1, which we can write 2 into 2 power m minus 2. Now the next thing that we can try to make a perfect square, I need 2 power 2m plus 2 into 2 power m plus 1. I need 1, but at the place of 1 I have a minus 2. So what we should add so that we can get a 1 here. So if I add 2 square, one more term I added in the number, so corresponding digit is 1 again. So you can see 4 minus 3, now it is 1. It becomes 4 minus 3, that is 1. So we get 2 power 2m, 2 into 2m plus 1, isn't it? So that is basically becomes 2 power m plus 1 square. Now here I have to definitely write that m is greater than 2. M is greater than 2, because these are represent different place values. So 2 power 2m is different than 2 power m plus 1, and 2 power square should be different than that 2 power 2m place value and 2 power m plus 1 place value. So I can say m is greater than 2, or we can say m is greater than equal to 2 also, because we are using m plus 1 and 2m. If m is greater than equal to 2, then these place values are different than 2 power 2. If m is greater than equal to 2, I can write this right hand side in this form. So here m is any number greater than equal to, so I can say there are infinite many values of m, isn't it? As this is true for m greater than equal to 2, so I can choose m is 2, 3, 4 and so on. So I will get a infinite such numbers. Okay, wait. We have to prove that it is equal to n square plus 1. So here what we get, we are getting only n square. Okay. So means we need one more thing here that we can, I think, easily pick. Like if I use 2 in that, so if we are adding one more place number, then the corresponding digit is 1. So you can see the effect is plus 1 again. So that is becomes now n square plus 1 type number, right? So right hand side becomes n square plus 1 type number that we need, right? M greater than equal to 2, you have a infinite many such numbers which are of a form this one. So that we proved for b is equal to 2. Now if b is greater than 2, if b is greater than 2, now we are picking the case when b is greater than 2. And we have x square plus 1, or x square is congruent to minus 1 mod of b minus 1. Okay. So using this information that if we have a such number x, we have to prove that there are infinite many such numbers for which this is for which the above property is true, that n square plus 1 is equal to this form, or we can say a number minus its sum of digits is n square plus 1. And basically we get this condition from there only, that this must be true, that x square is congruent to minus 1 mod b minus 1. Now if we try to like what we have here, x square plus 1 is equal to like am b power m up to what we can say a1b, no, minus summation of ai. So if we try to make a square from here only, can we do some modification in this to get a square? If we are able to make a new square from this condition, x square plus 1 is equal to this, like if I add b power 2m, or I can say b power 2k, both side, and saying that k is greater than m, and saying that k is greater than m, so b power 2k we are adding both side. But again, to satisfy this condition of our right hand side, if we are adding one more place value like b power 2k, the coefficient corresponding coefficient we have to subtract na? Because we have a digit sum also. So we can say b power 2k minus 1. So you can see this will cancel out, and we have a b power 2k plus x square is equal to this. तो ये चीज आ गई. राइट साइड परफेक्टली फाइन है राइट हैंड साइड, क्योंकि यहाँ पे क्या हमारे पास नंबर इन अ बेस b माइनस सम ऑफ इट्स डिजिट्स. In a left hand side we have a this. Now to make it as a perfect square, what extra term I need is 2x b power k. So if I multiply with the 2x b power k, Now here we have a problem, because if I need 2x b power k term, so the value of 2x, the value of 2x is not 0 to b minus 1, no? Because if you see the number x for x square plus 1 is this 1, so we cannot definitely say that 2x lies between 0 to b minus 1. So means we cannot proceed in this way to get a number that is a square, right? So what we do, we use this information that x square is congruent to minus 1 mod b minus 1 to extract some what we can say a small number for which 2x is 0 to b minus 1, isn't it? From this information I want to find out a number, let's say y square. If x square is congruent to minus 1 mod b minus 1, if I am able to find out a number y square for which 2y is 0 to b minus 1, then I can again use that above method to make a square, right? So basically if you see this information, this gives us that minus 1 is a quadratic residue of b minus 1, isn't it? Minus 1 is quadratic residue of b minus 1, isn't it? So we got this. Now let's see the next slide. So we have minus 1 is quadratic residue. So I can say that there should be a number y for which we have y square is congruent to minus 1 mod b minus 1, and y should be between 0 to b minus 1. No? Y should be greater than equal to 0 and less than b minus 1. Obviously y cannot be 0, so I can say y is greater than 0 and less than b minus 1, isn't it? And in fact there is a one more thing in a square residues. Like if I say y is there, then b minus 1 minus y, this one and this one, both square is congruent to minus 1 mod b minus 1, isn't it? If y square is congruent to minus 1 mod b minus 1, then this is also, because b minus 1 minus y square, you can see it becomes minus y square mod b minus 1, which is again becomes mod of sorry, y square mod b minus 1, which is minus 1. So if you have a one number y that is between 0 to b minus 1, that square is minus 1 mod b minus 1, then there should be another number also, that is this one. Now this sum is b minus 1, no? Y plus b minus 1y is equal to b minus 1. So I can say if one of them is less than equal to b minus 1 by 2, then another is greater than equal to b minus 1 by 2. So I can say one of them is definitely less than equal to b minus 1 by 2. So if I assume this is true, right, without loss of generality, if I use this one, that y is less than equal to b minus 1 by 2, and we have y square, is congruent to minus 1 mod b minus 1, or I can say y square plus 1 is a multiple of b minus 1. Now can we see a condition on a? Because y is less than equal to b minus 1 by 2, then where is y square? Y square is less than equal to b minus 1 square by 4. So y square plus 1 is less than equal to b minus 1 square by 4 plus 1. So now I can uh, put a find a constraint on a, because y square plus 1 is a times b minus 1, which should be less than equal to, so a is less than equal to b minus 1 by 4 plus 1 by b minus 1. But definitely it is should be an integer, right? As we know, this should be integer. So a is an integer which is less than this number, and clearly the value of a is a less than b minus 1, isn't it? Because this value is less than b minus 1, so clearly this value is less than b minus 1. Now we use this now we use this to make infinite many squares in a base b. So we have initially y square plus 1 is equal to a times b minus a. So this is a number in a base b and this is its digit. Now if I add b power 2m, if we add, then we have to subtract its that digit also, that is 1 only. So you can see in the right hand side, left hand side, we have a b power 2m and y square is equal to b power 2m plus ab minus a plus 1. Now if we go for 2ybm, next thing we try the 2ybm thing. So if I add 2ybm, then I have to subtract 2y also, because that we know that if we are adding uh, an place value in a number, then we have to subtract its corresponding digit. So same thing we can do in a right hand side. So provided this value is 0 to b minus 1, and this should be, because we know the value of y is 0 to b minus 1 by 2. We have seen that y is less than equal to b minus 1 by 2. So 2y is less than equal to b minus 1. Is we can perfectly do this. So the right hand side is again following the condition that number minus its digit sum. In the right hand side we are trying to make a square plus 1. So here we get a 3 terms that are perfectly fine, but we got a one more value, that is 2y, which is not uh, we want here, because at the place of 2y we need a plus 1. Means I want to create b power m plus y square plus 1, right? So means that is not we are getting. So what else we can do? As we are getting 2y, so I can further go for this square. So if we try to make this one, that is b power 2m plus y square plus 1, and then plus 2 power bmy, and that is minus 2y minus 2bm, right? So if we try to create this, and if you simplify this side like this one, if I add these two, it becomes 2y minus 2 times b power m. Now as y is less than equal to b minus 1 by 2 na, so where should be 2y minus 2? 2y minus 2 will be less than equal to b minus 1, definitely na? 2y minus 2 is less than b minus 1. So what we do, we do a modification in our step. What we are trying to add now, we are trying to add 2y minus 2 b power n. So if we are adding it, we have to subtract the coefficient also. So same thing we can do in a right hand side. In the right hand side we have a number minus its coefficient sum. Now are we getting this formula like b power 2m plus y square plus 2y minus 2bm minus 2y plus 2? So I think yes. So by 2, b power 2m plus y square plus 2y and minus 2 times bm minus 2y plus 2. Plus 2 can be written as 1 plus 1. No? So right hand side is as it. So that will become bm plus y minus 1 whole square plus 1. So clearly we can see that we write the number in this form, and the right hand side is basically a number in base b minus sum of its digits, isn't it? So if we have a number x, from there we get a number y, which is a quadratic residue, and y is 0 to b minus 1 by 2. Then from there we comment on this that we have a number this also. So m uh, again you can say one more thing in this as b power 2m. So you can see m is greater than equal to 2. Okay, because b power 1 is already used, so m should be greater than equal to 2. We get the desired answer. So that is a infinite many numbers. If you have one number, you have an infinite many numbers.